Welcome to today's virtual seminar, Unlocking the Secrets of Beef Jerky with Water Activity. The goal of this virtual seminar will be to be able to provide information and an explanation of why you are able to make and process beef jerky, what is the secret behind it, and that is dependent upon water activity and the power that water activity brings. And of course, the process of being able to make jerky has been known for many generations. It was known very early on that if you wanted meat to be able to last for any amount of time, there had to be a certain amount of processing that was done. And through trial and error, figured out that there are different ways that you could be able to do that. So, for instance, if you were to have fresh meat, if you want to keep that meat for any amount of time, you either have to place it in a refrigerator or you have to keep it frozen. And in an unfrozen condition, even in the refrigerator, it has minimal shelf life. We're talking about days, maybe a week of shelf life under those conditions. Very high moisture for this type of a product. So, which is great if you want to take a steak out and fry it up or barbecue it up on the barbecue. But what if you want to be able to have a meat product providing the protein that's provided by meat, but be able to have an extended shelf life where you could keep that product for weeks, months, and be able to have a safe product? Well, there has to be some sort of a processing, and that's this whole concept of why you would make jerky out of fresh meat, why you would create these shelf-stable types of meat products. And when you go through this processing, you create a meat that is shelf-stable, which means that you can buy it off the shelf as opposed to from a refrigerated portion of the store. And then the shelf life, now we're talking about, as I said, weeks to months for that type of a product, and a much less moisture in this type of a product. Of course, it has a very different texture than fresh meat necessarily would, although after cooking, of course, of fresh meat, there's obviously a change in the texture of that product as well. But the big difference here is that this processed meat product is now shelf stable and has an extended shelf life. So what processes do you go through to be able to take fresh meat and turn it into ready-to-eat meat or shelf-stable meat? And the basic steps here are there's a heating process often involved, not always. There will be typically a drying process where water will be driven from the product. And then there's often even a brining step where there's salt maybe is added in various forms, along with flavors that give it a distinct taste. There may be a fermentation process involved. That's not always the case, but for some types of shelf-stable meats, there will be a fermentation process, and we'll talk about why that is. And there also may be additives that are added, naturally occurring or synthetic additives that will also allow for extended shelf life. So these are the processes that you would go through to turn a fresh meat into a shelf-stable meat. So if we think about just moisture control, and that's really what the problem is with a fresh meat product in terms of its shelf stability, is that it just is very high moisture. It has a high level of water present. And so what kind of steps can you take from a processing standpoint in order to turn a fresh meat into a shelf-stable meat? And there are some basic ways that you can approach this. One is that you can remove water. And that's just a dehydration process. It's a very common process. Can involve high levels of heat, or it could involve exposure to very low humidities. The idea, though, is to create a situation where water will be removed or leave a fresh meat product. Another way is that you could bind the water in the product through the addition of what we call humectants. And humectants are things that would be added as ingredients that like to interact with water. And when they're placed in the product or in a jerky product, then they preferentially take the water and chemically interact with it. And as we'll see, lowering its energy and causing a lowering of water activity. You can affect the water structure, which affects its availability for microorganisms to grow, such as heating to drive it out, or freezing it, or applying pressure. All have the effects of being able to affect that water structure. And then you can, of course, if you can't do any of those things, then you can always refrigerate the product, keeping it at low temperatures, which then slows down all processes in the product that could lead to the end of the shelf life, including microbial growth. And of course, it'll be important to provide good packaging, a good moisture barrier, is another way to control moisture, because any exposure to external atmosphere or the ambient conditions will result in changes in the water conditions in the meat product. So those are some basic concepts of how to try and turn a fresh meat product into a shelf-stable meat. So the question then remains, how do you effectively track these moisture control processes provided by the application in shelf-stable meats? And even further, how does the USDA, from a regulatory standpoint, how do they suggest you account for these moisture effects or these processing, the moisture processing tools when you develop a HACCP plan? And if you reference the USDA website, and of course the USDA in the US is the organization that regulates the processing of meat products, including shelf-stable meats. And the USDA has gone to a complete HACCP approach to being able to assure the safety of different types of meat products and other products that they have oversight on. And HACCP, of course, stands for Hazard Analysis and Critical Control Points. And the point of this program, as a safety program, is to identify these critical control points that allow for a manufacturer to ensure the safety of their product. It's a risk-based program as well as a preventative program, as opposed to a reactive program, which has lots of benefits in being able to supply the safety that's required. So within the development of one of these HACCP plans, of course, one of the steps is, or maybe the most important step, is to identify those critical control points. So in terms of moisture and moisture control, then it's important to be able to identify a critical control point for moisture control. So what is that critical control point according to the suggestions that are offered by the USDA? And they actually offer generic models for guidelines for those people who are manufacturers who need to develop a HACCP program. And specifically for jerky type products, they have what's called Generic HACCP Model 10. And you can access this from the USDA website. And if you look in that general model, what you'll see in terms of critical control points when it comes to moisture control is that the tool that is used is water activity. And in times gone by, there was a use of what's called the moisture protein ratio, or MPR. You'll notice in these new HACCP guidelines that is no longer considered an acceptable critical control point. Instead, it is all based upon this thing called water activity. So what is water activity? This really holds the key when we talked about unlocking the secrets of making a shelf-stable meat. And this really is the key, is to have an understanding of water activity, because that is at the root of how you can make a shelf-stable product. So let's start off by identifying and defining what water activity is. In order to describe water activity, we have to go back to fundamental thermodynamic principles. And from those fundamental principles of thermodynamics, we can learn about ways to be able to figure out the energy of any kind of material. Thermodynamics deals with energetics, whether things are going to happen spontaneously because they're energetically favorable. And so in terms of energetics, we can derive from those fundamental principles a method or a way to be able to describe the energy, in this case, of water. And what that tells us is that if we want to know what the energy of water is, we need to know something about its escaping tendency, which is called the fugacity or ratio of fugacities. And this all comes from what's called Gibbs free energy. But beyond that, in terms of a practical sense, what we find from those thermodynamic principles is that water activity, or the activity of a material, is related to this escaping tendency of water, which then tells us about the energy of water, which means that water activity, in its pure definition, is a measure of the energy status of water in a system at a point in time when the measurement's taken. And that's the definition we use. We stay away from the terms free or bound water, which are often used in conjunction with water activity or available water in terms of availability to microorganisms. But that truly doesn't describe what water activity is telling us. Plus, those terms don't have scientific meaning. They can mean different things to different people. So instead of saying that water activity is a measure of the free water or the bound water, we talk about it in terms of energy. And when talking about in terms of energy, of course, the terms free and bound do have some meaning because they are related to the energy of the system. But to avoid confusion, we're going to stick to this definition that water activity is the energy status of water in a system. So how do you look at energy then? Well, we know again from our fundamental principles of thermodynamics that if we want to know something about the energy, in this case of water, we need to know something about how readily it can escape in the vapor phase. As something has more energy, or water has more energy and has more kinetic energy, it has a more likelihood that it can escape from a given product into the vapor phase. And so if you reduce the overall energy of the water in the system, you'll have fewer water molecules that can escape into the vapor phase. When water molecules, if I were to take a sample and put it inside of a sealed chamber, when those water molecules escape into the vapor phase inside of a sealed chamber, they will eventually come to an equilibrium. And at equilibrium, they will exert some sort of a vapor pressure. And that vapor pressure is going to be determined by the number of water molecules that are having enough energy to escape into the vapor phase, which tells us then that if we know the vapor pressure above a sample of water, that will tell us what its energy is, and so that will also tell us what water activity is. So water activity is determined or calculated by taking the vapor pressure of water above a sample at a certain temperature, and it's key that it's at a specific temperature, and then dividing by what the vapor pressure would be of pure water, or what we call the saturated vapor pressure, at that same temperature. And that's how we get water activity. So if we want to know something about the energy of water, we need to figure out what the vapor pressure is above a sample and compare that to the vapor pressure of pure water. If they're the same, then you would have the same number in the numerator as the denominator, which of course gives you a value of 1, which means the water activity or the energy or the relative energy of water, of pure water, is 1. That's our standard point or our reference point. So the water activity of pure water is 1 as the energy of the water goes down due to things happening in the product, such as interactions with things like humectants that we talked about. As those chemical interactions occur, it reduces the energy of that water. That water that's interacting with those different polar materials like sugar and salt no longer have enough energy to escape in the vapor phase, don't contribute to the vapor pressure. Consequently, there's a reduction in the vapor pressure above the sample, which causes the water activity to then go to some value less than 1. And it will continue on down. So we can say that at a water activity of 0.5, while we can't say that that means there's 50% free water and 50% bound water, because those are not quantitative measurements, that would not be correct. But it is correct that at a 0.5 water activity to say that the water in that product has 50% of the energy overall that it would have if you had pure water. And that provides valuable information because it tells us what the water is doing from a relative sense inside of a product as compared to what would happen if you were just dealing with pure water. And it ends up that this is similar to the way that you calculate relative humidity, such that the equilibrium relative humidity, or the relative humidity measured inside of a chamber that's at equilibrium, is the same thing as water activity just divided by 100. It also means that ambient relative humidity, while not necessarily a water activity because you don't have conditions of equilibrium, does have an impact on a product based on its water activity. For instance, if you subject a product that's at a water activity of, say, 0.8 to conditions where the ambient humidity is 30% or equivalent to a 0.3 water activity, water moves from high energy to low energy, which means it will move out of the product to the environment and would continue to do so until it's very close to the ambient humidity. So the humidity is having an impact on the water activity of a product if it's exposed to it for any amount of time. So to further illustrate what water activity is and how it's measured, let's imagine that we took some sort of a product and placed it. Could be pharmaceutical, could be a piece of jerky, could be a food. But if we were to place that inside of a container and then over time allow it to come to equilibrium, water molecules will escape from the product into the vapor phase, and the number of water molecules that are able to escape into the vapor phase is being, again, dictated by the overall energy of the water in the system. And what is in that product, how much water is present, and what's that water doing? Does it have lots of things to interact with, like sugar and salt? If it does, then there'll be fewer water molecules that can escape into the vapor phase, and hence the vapor pressure that is measured at equilibrium, and again, equilibrium means that there's no net change in the number of water molecules in the vapor state over time. Under those conditions, there will be a specific pressure that will be exerted, and that's the vapor pressure over the sample. That's our numerator. And so we just need a way of being able to measure what that vapor pressure is to be able to get our numerator value. Then if we were to take another container and put in that container pure water, then over time it would come to equilibrium as well, and there'll be a certain number of water molecules in the headspace that are exerting a pressure, which we call the saturated vapor pressure, or the vapor pressure over pure water. That pressure, or the number of water molecules that are in the vapor state, is dictated completely by the temperature. So if you know the temperature at which you're measuring, then you can calculate or determine the vapor pressure of pure water. That's the denominator. You put the two values together and divide them, and you get a ratio, which is your water activity. So that's how water activity is determined. The more water molecules, the closer the number of water molecules above a sample comes to water, the closer that value will be to 1. And again, this has to be done at a constant temperature when both vapor pressures are measured. So how do you actually measure water activity from a practical standpoint? Well, the most common way of doing this is through what's called a chilled mirror dew point instrument. And the way that this works is that, and this is an instrument that you see pictured that's offered by Decagon Devices, the AquaLab line of instruments or brand of instruments. And this is our Series 4 TE instrument that's shown. And it uses a chilled mirror technique for determining vapor pressure. And how this works is, if you take a sample and you put it inside of a sealed chamber, and again, let it to come to equilibrium, and that will take a certain amount of time, usually typically 4 to 5 minutes for most types of materials. Can be longer, especially for high-fat materials. So sometimes shelf-stable meats can take a little bit longer because they do have a fair amount of fat in the product. But after that amount of time, you take a measurement of the dew point temperature of that chamber, or the conditions of the chamber when it's come to equilibrium with the sample. And you do that by cooling down a mirror until the point at which dew forms. And an optical sensor is looking at the mirror and knows when dew is formed, because the optical sensor's beam will be interrupted. And you measure the temperature at which that happens. That's the dew point temperature. From the dew point temperature, it tells us then, and can be used to calculate, what the vapor pressure or the partial pressure is above the sample. If we also know the vapor pressure, or the temperature of the sample at the time the test is taken, and that's measured through an infrared sensor, that sample's temperature then can be used to determine or calculate what the saturated vapor pressure is, or the vapor pressure of pure water. You take the two and divide them, and you get water activity, and that's how it's measured in these instruments. And it can do so in a very fast amount of time. There are no sensors that are requiring equilibration to the conditions. It's simply a direct measurement of the dew point temperature. So because it's a primary measurement, it's very fast. Fastest method for measuring water activity there is, and also the most accurate, plus or minus 0.003 water activity. And you can basically measure the entire range of water activities, and it's very reliable. The only things you have to be careful about are two things. One is you have to keep it clean. If the infrared sensor or the mirror are contaminated, it can cause it to give erroneous readings, but you can check that with water activity standards, salt standards that are provided by Decagon. And when they aren't reading correctly, of course, you go in and clean, and then it should start reading correctly. The other thing is that if you have volatiles present, such as propylene glycol or ethanol, these can also interfere with the readings of the chilled mirror system. The alternatives of a chilled mirror would be to have a chamber where it comes to equilibrium, and then have an RH sensor in that chamber to measure the equilibrium relative humidity. We described that divided by 100 is water activity. So if you could just measure the relative humidity conditions at equilibrium, that would also give you water activity. The problem or downfall of these types of systems is that the capacitance sensor is a secondary method or way of being able to determine water activity, usually by tracking the electrical changes in some sort of a polymer. And the real disadvantage is that that polymer, in order to give correct readings, has to have come to full equilibrium to the conditions in the chamber. And that has a certain time associated with it that limits the speed of any kind of measurement that's done using a capacitance or a relative humidity sensor based approach. And that's what the big advantage of the chilled mirror system. And taking a look at the Series 4TE instrument that's offered by Decagon, this is a very easy to use instrument. You basically put your sample in, close the lid, push the lever over, and in roughly 5 minutes you get a water activity value reported on the screen along with the temperature at which that was determined. And so it's a very easy to use system. Anybody who's used our benchtop instruments in the past used to be the drawer system. This now has a clamshell design, much easier to clean and to maintain. Also has onboard storage, so it saves your readings over time and you can then download them to a computer or access them using the instrument. Has administrator settings so that you can put in passwords, lock out users if you so choose. And it has a very nice tight seal on the chamber. So it's a very easy instrument to use overall as far as a benchtop instrument. And this, of course, is what we would recommend for most quality control situations, even in shelf-stable meats. This would be the preferred instrument for being able to track the water activity of the product. So just as an overview, how does water activity differ from moisture content? Moisture content is something that's used quite a bit in the food industry and still in even the shelf-stable meat industry, but it's a very different measurement. Moisture content is a quantitative measure of the amount of water present in a product, while water activity is a measure of the energy or of the water in the system as we've described. So one's a quantitative measure, moisture content, while water activity is a qualitative measure of the energy of the water. So very different measurements. Moisture content simply tells how much moisture is present versus water activity, which says what is that water doing in the system, how available is it for things to happen due to its energy. There is a relationship between these two measurements, water activity and moisture content. That's what we call the moisture sorption isotherm. So we have water activity on the x-axis, moisture content on the y-axis. So it provides us information of how much moisture can be present in a product at a given water activity. And notice that for these products that are shown, that's very different for every type of product. The shape and the nature of this relationship between water activity and moisture content is very unique to the type of material, and so it should be investigated experimentally for each type of product to know exactly what that relationship is. But each type of material has a different ability to hold moisture at a given water activity or a given energy state. And that's dictated by what is actually contained in the product. How much fat versus salt versus sugar and so forth and so on. The more polar materials present, the more water can be held at a given energy state because, again, it's a comparison of what the energy of the water is. How much water can escape in the vapor phase. You can have more water present if that water has something to interact with because then it's not going to escape in the vapor state versus something that has very little material, polar material, to interact with water, and then all the water is present has the full capability to escape in the vapor state or the full capability to be available for other things to happen. So it's critical to have an understanding of what is actually in the product in order to figure out how much water can be held at a given water activity. So what do you do with water activity? We figured out what it is and how to measure it, but what do you actually do with it? Well, the biggest thing is that you can use water activity, and by knowing what the water activity of product is, you'll know whether or not you can prevent the growth of the bad bugs, the pathogenic bacteria that can cause people to get sick. It's also very good for a quick test to know when you've reached the end of the processing that you need for a shelf-stable meat. It also is very effective at ensuring product consistency. If you always process to the same water activity, you should have a very consistent type of a shelf-stable product. And of course, it provides safety records for HACCP plans. If it's incorporated as a critical control point in your HACCP program, then maintaining records of water activity values for your shelf-stable product, your shelf-stable meat, then you have something to go back to and show that you were in fact meeting your critical control points for your HACCP plan. So how does it actually work? How does water activity prevent the growth of microorganisms? If we consider a microorganism as a semi-permeable membrane that's just surrounding a sac of solute, that's very simplified in terms of a microorganism. Microbiologists may not be too happy about that definition, but for the purposes of our discussion, it works very well. If we think about that semi-permeable membrane has a certain water activity on the interior for that microorganism. And in order for that microorganism to access the water that it needs for survival, and they all need that water for survival, it relies on the transport of water across the semi-permeable membrane from a high energy to a low energy. And that's the only way that water can move, is from high energy to low energy. It doesn't have the ability to move it otherwise. And so it relies on having a lower water activity on the inside of the microorganism than in its surroundings. And if it encounters conditions where that's not the case, such as shown in the slide, where in the interior is 0.95 water activity, but the exterior is 0.9 water activity, now water will not move in because the water activity outside of the cell is lower than it is inside. And this is called osmotic stress. And when a microorganism experiences osmotic stress, it stops growing because it's not accessing the water that it needs. And now it has to do some sort of an adaptive process to see if it can cause the conditions or the water activity inside of its cell to be lower than the surroundings, such that water will then preferentially move into the cell. So it has adaptive mechanisms it can use to try and do this. And basically what's happening is it's concentrating solutes, trying to bring in polar materials that will interact with the water to lower the internal water activity. And sometimes it has the ability to create these themselves, like amino acids, polyols, sugars, and sometimes it has to transport them in from its surroundings. Each microorganism has a unique ability to be able to do that, meaning that each microorganism can get its internal water activity down to a certain value, but then it can't get any lower. And that determines what its lower limit is for growth. If it can't get low enough to match its surroundings or get lower than its surroundings, then that microorganism will stop reproducing and stop growing. And it has to go into some sort of a dormancy state at that point and is not actively reproducing. So it won't reproduce or grow to high enough levels then that would cause an infection. And that's how water activity prevents the growth or proliferation of microorganisms in a shelf-stable meat. If it's processed to a water activity that's low enough, assuming that there is not enough inoculant left of microorganisms on the product, and that's good manufacturing practices, because water activity is not a kill step. It doesn't eliminate the organisms, it just prevents them from growing. But if you process it properly so that there are not enough organisms present to cause an infection, then over time, as that product sits in its package on the shelf, there are not going to be microorganisms growing to high enough levels that they could then cause an infection when a consumer eats it later on. So that's how water activity provides its protection for a shelf-stable meat. And it's been doing so for as long as those shelf-stable types of meats have been being made. People may have not known why or what's going on, but they knew that if they drove water out, it would keep the product stable. And that's because it would lower the water activity to a level where those organisms can't grow. So over time, they wouldn't proliferate and grow, and it wouldn't make anybody sick. So that's the whole key behind being able to create a shelf-stable meat product. It's water activity. And here's just a listing of where those growth limits are for the different types of pathogenic bacteria. These are the bad guys, the bad bugs. Notice that each one of them has a little bit different. Some of them are the same, but they each have a water activity level below which they cannot grow. And that's indicative of their individual capabilities to be able to adapt and lower the water activity of their internal conditions. And so each one will have a specific point where it stops growing. If you can maintain water activity of a product or process it to a water activity lower than these growth limits, then those microorganisms will not grow, even if everything else is optimal, because these were determined with pH, with temperature, all of those things optimal for the growth of the microorganisms. Notice here, one of the biggest ones in shelf-stable meats that causes problems, of course, is Listeria. Notice that Listeria stops growing at 0.92. If you can process your product free of Listeria to a water activity less than 0.92, over time it will not grow Listeria on the product such that it could then get somebody sick. Now there's actually an interaction that goes on, a synergistic effect of water activity with pH. And some types of shelf-stable products, meat products, are a fermented product, which causes the pH to go down. If you can process, and there's two tables that are included in, and this is the FDA food code, so this isn't necessarily USDA, but it is scientific background that will be helpful when setting up your HACCP program, because it provides evidence of where those critical points are for the growth of those really bad bugs. And it has two tables that you use. This first table is assuming that you've had a kill step, a very high heating process on your product, and if that's the case, as long as you're below 0.92 water activity, your product is considered to be shelf stable, no matter what its pH is. If you process below 4.6 pH, then your product is shelf stable regardless of the water activity. But you can even be higher on both of them if you have both a pH effect and a water activity effect. So it's important to have an understanding of which control factor is being used, or what we call a hurdle, which is is where the idea of HACCP or critical control points came from. Do you have enough hurdles in place to be able to prevent the growth of the organism? If you don't, in the areas where you find in the matrix where it says PA, stands for product assessment, that's where you have to have used a preservative system and then prove that that preservative system actually prevents the growth of these bad bugs. If you're less than 0.92, you're safe though in terms of having a kill step and then subsequently packaging, because you've only have to worry about spore formers and that they all stop growing at water activities less than 0.92. You also are, in this case, controlling the growth, as we showed, of Listeria. Now, if you have a product that does not have a kill step, then the change is a little bit. It has to be down now below 0.86. You have to worry about staph. So less than water activity of 0.86, the product would be considered shelf stable regardless of the pH. If you're less than 4.2 on your pH, then it's safe regardless of the water activity. But again, you can be at higher levels of each as long as you have a combining effect of those hurdles. If you have a little bit lower pH, you can have a little bit higher water activity and still be considered shelf stable. So it's all about connecting or figuring out in the matrix where the product lies, and then using this information as a way of backing up the fact that your product would be shelf stable under those conditions that you're processing it to. So let's just take a quick look here at what the water activity of different products. This is a kind of a busy slide, but it's provided for your information just to show how different the water activities are of ready to eat, if you will, or processed meat products. Some are very high water activities. It will typically be a refrigerated product until you get down to some of the water activities that are below 0.92, where now you can be considered shelf stable. Notice that there are very different amounts of moisture as well. Each of these products is processed or sold as a type of shelf-stable meat product, but the differences in water activity are very high, as well as the amount of moisture that's left in those products, which shows that there are lots of different processing steps that are out there and available in order to create these shelf-stable meat products. But the focus is always on what is that water activity. That water activity tells you, is that product shelf stable, or does it have to be refrigerated, and is it a good product? And then here's just a continuation of that list. Again, for your reference, just to give an idea of what water activities we're talking about. And as you see, in general, the water activity of these types of products is typically going to be between about 0.7 and 0.85 because it has to be below that critical level for those pathogens to stop the growth of those pathogenic bacteria. There are some that are a little bit lower. The one key thing to keep in mind is that above 0.7, these products can actually still mold. So the water activity growth limits for the spoilage molds is below 0.7. All organisms stop growing at 0.6, but between 0.7 and 0.6 is just xerophilic and osmophilic organisms that grow. And so the practical limit is 0.7. So all of these products that have been processed to water activities higher than 0.7 have the potential to mold. And there's different ways that different brands have chose to address that. Sometimes it could be through a preservative system. Sometimes it could be through refrigeration. Sometimes it's through vacuum packing. But it is something to keep in mind that even though these are safe from a pathogenic bacteria, they're not going to get people sick. People also aren't going to not want to eat the product if it's got mold growing on it. So how do you know whether to refrigerate or not? Notice that if you were to go out and do a survey of the different types of shelf-stable meat products, there are some that have the note on there that you should refrigerate after opening, or that you should use them within a certain number of days. And why is that? And there are some who do not have that message on them that essentially say they don't have to be refrigerated. And it comes down to this idea where at a water activity that's typical for most of these shelf-stable products, again, that 8.5 to 0.70 range, is an area where spoilage molds will grow. And so either you have a choice of putting in some sort of a preservative, like, and you see in these ingredients, the sodium nitrates often are added as a preservative, as well as the sodium erythrobate is added as a preservative. So if you have a preservative present that's effective against mold, then you would not have to put the note on there that you would need to refrigerate. If you don't have an effective preservative system against mold and you process it to a water activity higher than 0.7, you have to have some way of being able to address that, either by limiting the shelf life of the product, such as saying to eat it before 3 days, or requesting that it refrigerates. Refrigerated temperatures, of course, slow down mold production. Or you have to have some sort of way of being able to restrict oxygen, which may work as you package it. If you vacuum pack, you restrict oxygen. That has two benefits. One, it prevents mold growth. Molds won't grow without oxygen. The second is that it limits rancidity through lipid oxidation. But of course, when the package opens, then it's exposed to oxygen, which only protects it until the point at which the package is open. And that's really what comes down to determining whether to refrigerate or not. The other factor for refrigeration is to slow down chemical reactions that could occur in the product that could end its shelf life. Even if it never molds, there isn't any microbial growth, no pathogenic bacteria, there are other factors that will certainly end the shelf life of this product. All products have a shelf life. They're never in a completely stable condition. And what actually ends shelf life is determined by how the product is processed. So for a lot of jerky products, what really ends the shelf life isn't mold, isn't microbial growth, it's rancidity. It's the product going to and developing off flavors or off smells that a consumer doesn't want to consume that product. Hence, its shelf life is over. And of course, the biggest one of that is rancidity, the lipid oxidation. Because of the high amount of fat present in a shelf-stable meat product, it is very susceptible then to lipid oxidation, especially because of its high water activity. And lipid oxidation, as well as all other types of chemical reactions that could potentially end shelf life, like browning reactions, hydrolysis reactions, nutrient degradation, all these things that could lead to a product not being or ending its shelf life are affected by water activity. In general, as water activity increases, so does the rates of these reactions. And so at water activities of 0.7 to 0.85 for these shelf-stable meats, they are in the prime range for the highest rate of reactions for lipid oxidation. So that's the other reason why a product may be refrigerated, is to try to slow down that oxidation process to prevent the product from going rancid and ending its shelf life. So again, that's based on water activity as being a way of identifying exactly what is this product going to be susceptible to. But of course, you got to also factor in texture and maintain the textural properties that are desired for that product. So how could you control water activity in these types of shelf-stable products? Well, one way, of course, is to dry it, and that's a very typical way that these are processed, through a dehydration process. Place them in a dehydrator at very low relative humidities, drive water out, lowers the amount of water present, and consequently the water activity. But there are other ways too that can be used in order to lower water activity without necessarily having to remove any additional moisture. And that's often can be a very good thing, because moisture, of course, is weight, and these products are sold on a weight basis. Driving water out isn't necessarily always a great idea, because you're lowering the weight of the product. Plus, you're increasing the cost of the processing in order to drive that water out. So it's often valuable to be able to keep water in. What if you still need to lower the water activity? Are there alternatives? And there are, through the addition of what we call humectants. And the most common humectant that's used in a shelf-stable meat product would be salt and then sugar. And these are very effective humectants. They're very effective at lowering water activity. It's why they're often used as ingredients, in addition to, of course, the flavor properties that they offer. Another form of sugar or sweetener is high fructose corn syrup. Sometimes it may be sorbitol, maltodextrins, and even starch has an ability to lower water activity. Not as effective. Each one of these have their own level of effectiveness, and swapping ingredients straight across does not always result in the same lowering of water activity. So in an effort such as the efforts to try and reduce sodium levels, switching over to an alternative salt does not necessarily going to result in the same lowering of water activity. So be careful about which humectant you use. Each has its own unique ability to lower water activity. There are limitations to using these humectants, of course. One of them is, just we talked about, you use a lot of salt, you have a high sodium product. That's not necessarily favorable as people try to go to more healthy diets. Also, it provides organoleptic properties. Adding more salt is, of course, going to make the product salty. It's not always an option. Adding more sugar is going to make it sweet. Each of these have a solubility limitation to them, there's only so much that you can add to a product, so only so much lowering of water activity that can occur. You can, by adding materials, make them more reactive, such as to Browning reactions. Some types of humectants at high levels can be toxic, but in general, it's the art form of being able to create your right formulation, the right brine, is to figure out how to get the flavors you desire, but still have the same water activity lowering that you need from these humectants. So let's take a look at an ingredient list and for a common type of jerky product and see what was present. Of course, the top ingredient would be the meat, but then notice that in the case of this particular product, that corn syrup solids is the next ingredient. That's the sweetener for flavor, but it also provides water activity lowering. That's a humectant. It is going into the sample when it's added, and it's interacting with water and preferentially taking that water, binding it from a chemical standpoint. That water no longer has a high enough energy to escape into the vapor phase and hence has a lower water activity. Next is dextrose. Dextrose is also a very good humectant. It's a sweetener source, will lower water activity as well. And then notice that the next one is salt. And again, salt being a very effective humectant. So after meat, the next three ingredients, while they also offer organoleptic properties, are all important for determining what the overall water activity would be. So that's their purpose, among others, to be added to these types of shelf-stable meat products, is to be able to help control that water activity, making them more shelf-stable and extending their shelf life. Let's just see how this works as an example. We made and processed here at Decagon 2 batches of beef jerky. One of them we did using just a normal recipe, normal formulation. Salt source was soy sauce, had a certain amount of salt, certain amount of sugar added to this product to make a nice beef jerky product. Processed that to a water activity of 0.785, had an acceptable texture, did a taste test. Everybody deemed it as being acceptable. Moisture content here was 15% when it was processed. Now, what if we add 10% glycerin to the product? And we process it again to 15% moisture content. The water activity, instead of being 0.785, because it has glycerin added, has now a water activity of 0.585. Notice how different the water activity is because of the addition of the glycerin. Glycerin, or glycerol, is a common product. It's food grade approved, very effective at lowering water activity. At lower concentrations has very little effects on organoleptic properties, but is very effective at lowering the water activity, and it was deemed as having acceptable texture as well because of the plasticizing effects of adding the glycerin. And we even tried to do a prediction. There's a way of being able to predict what the water activity will be when you add a certain amount of solute like glycerin to your product. We predicted about 0.684 using a combination of the Roche and Norris equation, and which was actually fairly close to our 0.585. It's not perfect. Certainly any prediction is not perfect, but it would give us an idea that we could lower the water activity using that added glycerin to this beef jerky product. And we have those tools available to anyone interested, where the most effective thing is perhaps being able to figure out if you need to go from a certain water activity down to a more preferred water activity. How would you do that by adding a solute? How much would you need to add? And you can actually do predictions and figure out what that is. Now let's take a look at the drying curve for this jerky that was processed. And so we're tracking, again here, weight change, figuring out what the weight change is over time. Notice that there's a very, that right off you see the weights to starts changing even after a short amount of time. And this is, again, is water loss that's occurring during the dehydration process. But not a lot of change in the water activity. It's somewhat noisy at that high when it's initially starting to be driven out. But the water activity is still remaining fairly high in the unsafe zone. And so you're getting a fair amount of moisture loss, but not a subsequent change in water activity. And that's over the first initial part of the process. But then notice at the end, now you've reached a point where you're not experiencing as big of moisture content changes, but now the water activity is starting to go down. And it's going down at a fairly quick rate. And that's the critical time of where you're going to identify where you're going to, how you're going to end the processing, or what point you're going to end the processing. And if you're tracking water activity, you can pinpoint the exact point at which the water activity is down to a safe level. And as long as it provides the textural properties that you want, that product would be deemed safe, it's shelf stable. That could be or may be the end of your processing. And so what this indicates, this graph, is that you need to be very careful towards the end of the processing if you want to actually be able to fine-tune and pinpoint the point where you've reached a safe water activity and then stop the processing at exactly that point. And this can be shown further if we take a look at the moisture sorption properties of jerky. These are that water activity versus moisture content relationships for several different types of products. Notice that initially there is a big difference or loss in moisture content, almost a 15% loss as you go from 0.9 water activity starting out to 0.8. And so that initial loss is very steep, very big changes in moisture content for small changes in water activity, which is why in our previous slide there was a delay in the loss, the change of the water activity, even though the moisture or the weight level was dropping fairly quickly. And it shows it in this moisture sorption curve. So over that first initial time of drying, you're moving a lot of water out, but not necessarily change the water activity. But then you get to a point where the curve starts to flatten out more. And now with every removal of water, you're getting a bigger change in water activity, which if you want to use it as a process control indicates that after a certain amount of time, you're going to have to start tracking that water activity if you want to be able to end it at a very specific point. And then listed in our table here, this is the amount of time that it took for each of these different materials to reach equilibrium, and that's identified by a certain trigger value of weight change over time at each one of the water activity levels. And doing a comparison, you can see that depending on the product that you're working with, there are very different amounts of time that are required in order to achieve the drying process that has to happen. And in fact, you could use this information, it's called kinetics absorption, to figure out and do a prediction about the drying times that are required if you have that information. We offer an instrumentation that does these curves and generates this information called the AquaLab VSA. If you're interested in finding out more about that, please contact Decagon Devices. Now let's end by just looking at a case study of what could happen by over drying your product. And this is a situation where you may not be monitoring water activity closely during processing and ending specifically on a water activity value that's deemed to be safe. So let's imagine that we have here a small jerky processor. They sell 100,000 pounds of processed jerky per year. They sell that product, let's say wholesale, for $15 per pound after they've processed and made the product. Without water activity monitoring, and they were just going down to what felt right or maybe off of a moisture content, and they processed to 0.785 water activity, that processing would result in a 55.3% loss in weight as you were drying it out. Final moisture content would be 35.2%. If you were after having all your processing, if you were doing about 100,000 pounds per year, then the income from the sale of that product for $15 per pound with this processing step would be $1.5 million. Now let's say that you were tracking water activity as a process control and you only processed to 0.85 water activity where it's deemed safe, and that processing, those changes in water activity didn't result in any significant changes in texture. And this processing now results, instead of 55.3%, you only get a 53% loss in weight due to your processing. So you have an additional 2% gain in weight for your processing over the 100,000 pounds per year that you were selling. Final moisture content, 38.2% rather than 35.2%. Now you get to sell for your efforts, you get to sell your product because you'll have more of it now for $1.533 or $1,533,000. So if we sum that up, so you have, by over drying to a lower water activity and removing more water out of the product, you have the potential of a $33,000 loss because you're putting in more inputs. So you're doing more work. So you would even be in an additional loss because you're doing work that's not necessary, and at the same time losing income equal to $33,000, all for more drying time plus more input costs to go from a 0.85 water activity to 0.79 with no additional added safety. They'll both mold, and neither one of them will support pathogenic bacteria. So the key take-home lesson here is that if you monitor water activity as a process control, you could make yourself $33,000 with less time inputs and less work inputs for a product. That's pretty easy money. And the final thing I want to talk about here is packaging. Packaging is a very important consideration for any type of shelf-stable meat product because you're processing or making a product that's typically at high water activities, and it will be exposed to ambient humidity conditions that are typically around 30 to 50% relative humidity, which means that it will have a tendency to dry out and lose moisture to its environment, affecting its texture and, of course, its shelf life. So packaging is a very important factor in shelf-stable meat products. It is possible, using information about that isotherm, water activity versus moisture content, and knowledge about how water moves, to figure out the permeability of packaging and identify exactly what packaging product you would need in order to achieve your desired shelf life, with the idea that you want to prevent the water activity of your shelf-stable meat product dropping below a certain water activity where its texture will no longer be deemed acceptable over time. So you identify where that water activity is, then using information about the permeability properties of the packaging, which you can actually determine using experimental data, or is typically offered by the packaging manufacturer in the form of what's called a water vapor transmission rate. Be careful, that's not a fundamental value, can't be plugged into equations such as Fickian diffusion, but it is possible to convert those as long as you know from the packaging manufacturer the conditions it was determined under. But you can then figure out what's the permeability of your packaging and actually do predictions about how much water activity is going to change for your product given a certain set of conditions it's exposed to. Or you can figure out what kind of packaging material you're going to have to be able to use in order to achieve or maintain the water activity of that shelf-stable product regardless of the conditions that it may be exposed to. And so these calculations are all possible. We have an Excel sheet that we've placed them in or built them into. You just have to plug in the values specific to your situation, and it does the calculations for you. If it's something that you're interested in, we can set it up and help you walk through it, whether you're an individual processor of shelf-stable meats, you're processing it out of your basement, or you're a large company and you're in charge of the packaging. We can help you either of those situations figure out exactly what your packaging needs are and whether or not you're spending too much right now for your packaging, or if you're not packaging with a good enough moisture barrier. So in conclusion, water activity is the key to making shelf-stable meat. The secret of shelf-stable meat that's been made for generations has always been water activity. You lower the water activity by driving water out, and that when you get to a certain water activity, it prevents spoilage by pathogenic bacteria that would make you sick. Water activity, keep in mind, remember that the definition is that it identifies the energy of water, and by doing so, it describes exactly why microorganisms can access it. It's because of the reduction in the energy of the water due to interaction with different types of ingredients like sugar and salt. And as such, it allows it to control that microbial growth. And then if you look into using water activity as a way of being able to monitor process control, it allows you to have tighter control over that and prevent loss that can come from over drying your product. That's just lost money due to increased inputs, wasted time, and losing income during the whole process. So think about that idea of being able to possibly incorporate water activity as a process control that could actually make you money, and certainly pay for whatever costs would be involved with the instrumentation that you would need. So I hope that this has been helpful and informative about describing the secrets behind shelf-stable meats, that it's rooted in water activity. Water activity is the key. We're happy to provide additional support and help in the area of water activity at Decagon Devices, and with the AquaLab brand. We are the world leaders in water activity measurement and water activity knowledge, and we're here to support and help you. And I appreciate your attendance today, and I thank you.